Assalamualaikum and hi everyone. In this video, we will present about crystalline solid. Before we begin, let us introduce our team members. The first member is Nur Kalisa binti Hairunizam. The second is Nurul Izzati binti Muhammad Arif. The third is Nura Anis binti Azmi. And lastly, my name is Nur Shahada binti Abi Manap. And together with my team, we prepared this presentation. Have you ever wondered why some solids have perfectly ordered structure while others don't? Today, we are going to answer that question. Our presentation has three main objectives. First, we'll compare crystalline and amorphous solid and see what makes them different. Next, we'll explore stoichiometric and non-stoichiometric defects, which are imperfections found in crystal structure. Lastly, we learn about the F center in NaCl, an interesting defect where a missing chloride ion traps an electron, causing the crystal to develop colors.
A crystalline solid is a material in which atoms, ions or molecules are arranged in a highly ordered and repeating pattern. Because of this regular arrangement, crystalline solids have a sharp melting point and a definite heat of fusion. Another important characteristic is that they are anisotropic, meaning their physical properties such as electrical conductivity or strength may vary depending on the direction. Common examples include diamond, quartz, and sodium chloride. Unlike crystalline solids, amorphous solids do not have a regular arrangement of particles. Their atoms are randomly arranged, giving them a disordered structure. As a result, they do not melt at one specific temperature, but instead soften over a range of temperatures. They are isotropic, meaning their properties remain the same in all directions. Examples include glass, plastic, and gels.
So, have you ever wondered why some metals are easily bent and the others harder? The answer is, it depends on their crystal structure. Let's understand their crystal structure first. There are three common structures, that is, body center cubic, which is BCC, face center cubic, FCC, and hexagonal closed back, HCP. First, BCC have 8 corner atoms and 1 atom at the center. This structure makes material strong and hard, but less ductile. For example, iron, chromium, and tungsten. Next, for FCC, the atoms located at the corner and the face of each cube. Since the atom packed more closely, FCC material is more ductile and easy to shape. For example, aluminium, gold, and silver. HCP has hexagonal arrangement with close-packed atoms. It provides high strength, but less ductile than FCC. Example is magnesium, titanium, and zinc.
And now I will explain to you about stoichiometric defects. Stoichiometric defects are a specific type of crystal imperfection. The word stoichiometric means that even though there are mistakes in the structure, the balance and ratio between the cations and anions in the atom remain exactly the same. Stoichiometric defects generally happen in one of 4 ways. The first one is vacancy defect. It is where an atom is missing completely from its assigned spot. Next, interstitial defect. It happens when an extra atom squeezes into an empty space where it does not belong. The third one is Schottky defect. A matching pair of one positive and one negative ion go missing together at the same time. The last one is Frankel defect, where an ion gets misplaced, leaving its original spot empty and crowding into a nearby gap. These defects occur in 2 different conditions, where vacancy and interstitial occurs in non-ionic crystal, while Frankel and Schottky happens in an ionic crystal. Stoichiometric defects give materials their useful properties. In vacancy defect, the density drops. This gives the remaining atoms room to hop around, enabling the solid state diffusion needed to harden metals. In interstitial defect, an atomic traffic jam that occurs blocks internal movement. becoming the reason why steel is harder than pure iron. In Schottky defects, the missing pairs leave behind open pathways that allows ions to migrate. This high ionic conductivity is the exact principle behind a solid-state batteries. In Frankel defects, there is no mass loss and density stays the same, but that displaced ion is now highly mobile. This ion mobility is the exact mechanism that drives traditional film photography. While none of these defects alter a material's chemical formula, they completely change how it behaves, and density changes tell us exactly what is happening in the atomic level.
Now, let's move on to the non-stoichiometric defect. Unlike stoichiometric defect, where the ratio of cation and anions remain balanced, non-stoichiometric defect happen when this ratio is no longer equal. In other words, the number of positive and negative ions is different. There are two main types of non-stoichiometric defect. First is metal excess. As the name suggests, the crystal contains more metal ions than expected. This usually happens because the defects such as missing anions or extra metal ions in the crystal. The second type is metal deficiency, where its opposite situation, some positive metal ions are missing from the crystal lattice. Even though ions are missing, the crystal still maintains electrical neutrality by changing the oxidation state of some of the remaining metal ions. So, a simple way to remember it, by metal excess equal to too many metal ions and metal deficiency equal to not enough metal ions. Let's look at those two in detail. Starting with metal excess defect, as mentioned earlier, there are more metal ions than normal. One common case is when an anion is missing from the lattice. The empty space doesn't stay empty. It traps the electron, forming what we call F center. The letter F comes from German word Farbe, meaning color. This trapped electron absorbs certain wavelength of light, giving the crystal its characteristic color. For example, NaCl, KCl, LiCl can develop color when they contain F centers. Normally, pure sodium chloride is colorless, but with this defect, it may appear yellow. Now, let's move to metal deficiency defect. Here, some positive metal ions are missing from the crystal lattice. To keep the overall charge balanced, some metal ions change to a higher oxidation state, which is why this compound often show variable valency. For example, NiO, FeO, and Fes. If you look at this diagram, you can see a missing metal ion called vacancy. Around that vacancy, some ions change their charge to compensate for the missing positive ion. So, the key difference is metal excess have extra metal ion or trapped electron, produce F center and color. Metal deficiency have missing metal ion composite by variable oxidation state.
Here's the example between stoichiometric and non-stoichiometric defects. Stoichiometric defect does not affect the chemical formula. Non-stoichiometric defect change the compositions. Stoichiometric defect include vacancy, interstitial, Schottky, and Frankel defect. Meanwhile, non-stoichiometric defects include metal excess and metal deficiency. These comparison help us classify this defect easily.
This slide explains why pure sodium chloride is white, but defective sodium chloride becomes yellow. In pure sodium chloride, all sodium and chloride ions occupy their correct lattice positions, so visible light is not absorbed. However, when sodium chloride is heated in sodium vapor or exposed to radiation, some chloride ions leave their lattice positions. The empty sites trap electrons and forming the F centers. These trapped electrons absorb certain wavelengths of visible light. As a result, the remaining reflected light gives the crystal a yellow color.
For the conclusion, Crystalline solids are important to inorganic chemistry because of their ordered atomic structures, which give them predictable and unique properties. Their study effectively bridges the gap between microscopic atomic arrangement and real-world material behavior. While perfect crystal exists only in theory, the real value of crystalline materials lies in our ability to understand, control, and apply both their structures and their inherent imperfections. Crystalline solids are everywhere, making them truly indispensable to both science and our everyday life.
These are the references we use to prepare this presentation. We refer to reliable journal articles and academic resources to ensure the information is accurate and up to date.
That is all for our presentation, Crystalline Solid. Thank you and Assalamualaikum.